Hi, welcome back to the lecture series on abstract measure theory. This is the second lecture on this course and today we will discuss the characterization of bounded variation functions. In fact, we will see that a function f from the closed interval ab to r is a bounded variation if and only if it can be expressed as the difference of two monotonic increasing functions. So now to derive this characterization, first we will discuss the following. Let's take this interval. Okay, let AB be a closed and bounded interval. Be closed and bounded interval, and let's take the partition, let P, which is equal to A equal to x naught x1 xn, that's equal to B, be any partition B any partition of AB. Okay, take any partition of AB and let's choose any point C in this interval. Let's choose any point. Let's C belongs to the open interval A comma B, that is this C lies between A and B. Okay, so let's take the interval AB, be a closed and bounded interval of real line, and let's take its partition of this interval P equal to the set A equal to x naught x1 x2, which is equal to B, be any partition of this interval, and let's choose any point C in this interval. Then this point C belongs to lies in one of the subinterval. Okay, it lies in one of the subinterval, obviously, because this partition divides the closed interval AB into n subintervals, and this C belongs to one of the subinterval among those n subintervals. So without loss of generality, let's assume that this C belongs to the ith subinterval. Okay, suppose assume that this C, it belongs to this interval xi minus 1 xi that is xi minus 1 less or equal to C, less or equal to xi. Now we choose the another partition which is obtained from the partition P actually. Choose this partition. Choose the partition P dash, which is equal to A equal to x naught x. In fact, you assume that this C belongs to the open interval xi minus 1 xi. So this is not here. So this assumption can be taken okay, strictly less. Okay, so choose this partition now, then choose its xi minus 1. Next point you choose C, then you have xi plus 1, then xn, which is equal to B. Obviously this partition P dash, it is a refinement of P. So then this P is subset of P dash. So for any partition P, we can always obtain a partition P dash like this: A equal to x naught x1 xi minus 1, then C xi plus 1 and xn, where C is any point in the open interval AB, and obviously this C belongs to one of the subclosed, one of its subinterval. Okay, because the partition P divides our interval AB into n sub-intervals. Okay, this C is lies in one of the interval. So assume that it lies in the ith interval, and from this we obtain the following partition P dash, which contains this point C also. It contains also the points of the partition P, all the points, and the one more point, that's C, which is not in that partition actually. So if C lies in the partition P, then this P dash is same as P. Then there is no need to write this P dash. So actually we are doing this for those points C which lies in the closed interval AB, such that those points such that point C is not equal to any of the partition point of the partition P. So from this then we can then we obtain the different partition P dash, which is obviously the refinement of Phi. So in general it may be equal if we choose any point C. Okay, if there is no restriction on this point C, then this P may be equal to P dash. So in general it's subset of. Okay, now let us see this. Let's take the following sets. Let capital V, it is a set of the all variations, where this P belongs to the partition of AB. Let's take this set. It's a set of all variations. Okay, if we vary the partition, we obtain the different variations, and this V, capital V, it is a set of all variations. Okay, now next we define one more set, that's V dash. It is also the set of the variations, but this is P dash actually, where this P is obtained, this P dash is obtained from P. P is the partition of AB. Now you can see that this V is actually, you can see this V is actually the collection of all variations, and this V dash is also collection of variations. It's also the collection of variations, but these variations, they also lie in this class because it is the collection of all variations with respect to any partition, as P dash is also the partition of AB. So we can see that this is a bigger class actually in general. So then we can see this V dash, it is subset of V. So this implies that the supremum over V dash is actually less or equal to supremum over V. But on the other hand, what is the supremum over V? It's actually the total variation. This is equal to the total variation of F, because V is the variations. It is the supremum of variations of the variations where P belongs to the partition of AB. Okay, so this is the total variation actually. But on the other hand, we have the following. But on the other hand, this for any partition P variation Fp, that partition having the partition points x0, x1 up to xn, it's equal to summation I runs from 1 to n mod of f of xi minus f of xi minus 1. Actually, I am trying to show that these two supremums are same. The supremum of V dash is same as supremum of V. Okay, so that's why then I will take the partitions which contain a particular point, and I will take the supremum over those partitions that will give the supremum over all the partitions. supremum over all the part, because the supremum was, they are the same actually. Okay, that I will see here, that will show here. This is the variation by definition, and that's if we expand this variation, it's equal to mod of f of x1 minus f of x naught plus you continue this process, and at the ith stage you will get f of xi minus f of xi minus 1. Then at the nth stage we have f of xn minus f of xn minus 1, and that's equal to mod of f of x1 minus f of x naught plus mod of f of xi minus f of c plus f of c, okay, minus f of xi minus 1. So adding and subtracting f of c minus f of c plus f of c, okay, plus mod of f of xn minus f of xn minus 1. Now let's apply the triangular inequality to this mod. It's like this: mod of a plus b. Mod of a plus b is less or equal to mod of a plus mod of b. So it's less or equal to. So I will write this term first, okay? Yeah, this mod. This is less or equal to mod of f of x1 minus f of x naught plus mod of f of c minus f of xi minus 1 plus mod of f of xi minus f of c. Okay, plus nth term f of xn minus f of xn minus 1. Let's have a look at this line first. This is mod of f of x1 minus f of x naught plus so on. Now we have applied here triangular inequality. This will be less or equal to mod of f of xi minus f of c plus mod of f of c minus f of xi minus 1 plus so on, plus that mod. Then I have interchanged these two terms. I have written here there f of mod of f of c minus first f of c minus f of xi minus 1, then f of xi minus f of c, then f of xi minus f of c here. Okay, but this one, these part x naught, x1, x2, so on up to xi minus 1, then c, then xi, then so on up to xn. This is the partition p dash, which is obtained from the partition p. So it's actually equal to the variation f p dash. So thus we have this variation fp is always less or equal to variation fp dash. So if you take the supremum over these partitions, so let's apply the supremum of this variation is less or equal to the supremum of these variations. Okay, but supremum over v of a b, it means the supremum of v, actually the set v which we have constructed. So this means the supremum of the set v is less or equal to this one. It's the supremum of the set v dash, but this is the total variation actually. Total variation of f is less or equal to the supremum of v dash. But earlier we have seen that this is also less or equal to. We have already seen this. Can get this supremum of v dash is less or equal to the total variation. But now we have seen that total variation is less or equal to supremum of v dash. So that means we have thus total variation of f is equal to the supremum of v dash. Now here the partition p, here the partition is the variation is the partition is of the interval ab, they contain the particular point c. Thus the total variation of a function ab, thus total variation means the supremum. Thus the total variation, thus the total variation of a function on ab, of a function on closure interval ab, thus in the definition, okay, thus in the definition of total variation, sorry, thus in the definition of total variation of a function on ab, the supremum in that definition, the supremum, because total variation is actually the supremum can be taken over partitions, can be taken over partitions, of AB that contain the point C. That's what we have seen, that contain, the supremum is same actually, that contain the point C, can be taken over the partition is of AB, because where the supremum is taken over the partition, but we'll that in that now definition of the total variation, the supremum can be taken over the partitions of AB that contain the particular point C. So this now suppose we have a partition P that contains the point C, obviously. Now let P, okay, let me write it precisely here, okay. Let P be the partition which contains the point C. Suppose it's equal to A equal to x naught x1, then xi minus 1, then suppose we have point C, then xi plus 1. This is the partition which contains the point C, okay. Be a partition of AB, okay. Then P1 which is equal to A equal to x naught x1 xi minus 1, then C, and P2 equal to, the first point is here C, now C, then xi plus 1 xn. These two partitions, this is the partition of the interval AC, and this one it is the partition of the interval CB, because xn is equal to B. Here xn is equal to B. Okay. Then these are the partitions, of AC and CB, and conversely if we have a partition of AC and CB, then we will get the partition of AB, and conversely if P1 Suppose P1 is equal to A equal to X naught, X1 so on up to say Xm equal to C, and P2 which is equal to C, equal to C C is obviously here Xm, then Xm plus 1 so on up to Xn which is equal to B, or sorry, they or the partitions of, or the partitions of AC and CB respectively, AC and CB respectively, then their union, okay, then their union is the partition of AB, is the partition of the closed interval AB. So that thus we have seen that given a partition P of AB containing the point C, this will induce the partition of the interval AC and CB, and conversely given a partition of the interval AC and CB where C is a point in the interval AB, then we will get the partition of the interval AB, which is actually the union of these two partitions, And one more thing, we have and for such partitions, that means P is equal to P1 union P2. For such partitions we have variation of the function f with respect to the partition P over the interval AB, which is equal to variation of the function f over the interval AC with respect to the partition P1 plus variation of the function f over the interval CB with respect to the partition P2. This is simple. If you expand this partition which contains the point C, then you have to break the sum at this point C, and you will get the two sums. So you will get two partitions, like two variations actually. One is the variation of f over the interval AC with respect to the partition P1, and second is the variation of f over the interval CB with respect to the partition P2. You can easily verify it. It's not too difficult. You have to expand this variation actually, or if you want to verify it here, let's check it. Let's see this. V of fp, it's equal to mod of f of x1 minus f of x naught plus at I minus minus stage we have here mod of f of c minus f of xi minus 1, then plus we have mod of f of xi minus f of c plus this one, it's equal to mod of f of xn minus f of xn minus 1. And you can see this one, it is a variation of the function f over the interval AC, because x0 is equal to a, and this is the point C here, last point. And this is the variation of the function over the interval CB, because here we are starting with the point C and xn is equal to b. So this is equal to the variation of the function f over the interval AC with respect to the partition P1, because P1 is the partition x0 x1 up to c, and P2 is the partition c then xi up to xn plus variation of the function f over the interval CB okay. So now let's take, thus we have the following. This is actually we have obtained this variation of the function f over the interval AB containing the point C. This is important. This the partition contains the point C. Okay, P, the partition which contains the point C, which is equal to variation of f over the interval AC. And variation of f over the interval CB with respect to the partition P2. If P1 is any partition of AC and P2 is any partition of CB, then P is the partition of AB. And conversely, if we have partition P of AB, any partition P of AB containing the point C, then this P1 is a partition of AC and P2 is a partition of CB. So let's take the supremum over all the partitions, okay, by taking supremum, by taking the supremum over such partitions, over we obtain, this is the total, this we have already seen, this is the total variation of f, okay, over the interval AB. Let's fix it, because here the intervals are, we change the intervals. It's equal to the total variation of f over the interval AC plus total variation of f over the interval CB. So this we have seen. This we have seen. Now let's define the function that we call the total variation function, and we will see that that function is monotonic increasing. So we have to apply this property, name this star, this property, okay. This is very important equation, okay? This star, total variation over AB is equal to total variation over AC plus total variation over CB, where C is any point lying between A and B. So now define a function. First, for this we have to assume that this f is a bounded variation. Okay, otherwise this function will not be defined. So suppose, let me erase this first. Let f be a function from closed interval AB to R, be bounded variation, be bounded. And one more thing that we can conclude from the previous equation, which is the following. Suppose function is a bounded variation over AB, then this is finite, therefore both numbers must be finite. So that means that function must be bounded variation on any subinterval, okay? On any subinterval, it must be bounded variation. It must be a bounded variation on any subinterval of AB. So let f be bounded variation on AB, so therefore it is bounded variation on any subinterval AB. Now define T. Let's define function capital T from the closed interval AB to R by T of x is equal to total variation of the function f, total variation of the function f over this interval a to x, okay, a to x over the interval x. Total variation of the function f, or we write it as we use this notation for total variation. This is also correct. Total variation of f over the interval ax. So this is a finite number because f is a bounded variation over AB, therefore it is bounded variation on any subinterval. So this is finite. So this is the real valued function. Here we show that this function t, because for each x we have some total variation, you can see this with the help of an example also. So you define any function, say, then you find its total variation. Say let's take example here, how to find this total variation function for any fixed point. Okay, so let's take this f of x equal to say x square. Okay, it's monotonic increasing on the interval 0 1, x belongs to 0. Let's find its total variation. Say I want to find t of 1 by 2, which is equal to total variation of the function f over the interval 0 to 1 by 2. And but we know that this function is monotonic and increasing, therefore total variation is equal to the f of the end point minus f of this initial point. It's equal to f of 1 by 2 minus f of 0, which is equal to 1 by 2 whole, that's 1 by 4. You can find it at any point, say 1 by 5, or say x in general, which is 0 to x, which is equal to x square minus 0, which is same as this function in fact. So if you want to, in general, you want to find it t of x, which is equal to total variation of f over the interval a to x, it's equal to x square. You can see it because function it's monotonic increasing function, therefore total variation is equal to the difference of the end values, the values of the function at the end points in fact. Okay, so that's f of it is 0 here, it is 0 to x. But suppose it's x square plus 1, then it will be f of x, which means x square plus 1 minus f of 0, that's equal to 1. In that case it's equal to x square plus 1. So suppose the function is x square plus 1, then I think it may vary at that moment. So total variation function is same as the function f in fact, it's equal to fx in that case. But in general it's not equal to the function fx itself. You can see examples for that. So let's try to show that this function is monotonic and increasing. We show that t is monotonic increasing. So let's choose, let uv be any point in the interval a b such that u is less than v. We will show that t of u is less or equal to t of v. Monotonic increasing, we show that t of u is less or equal to t of v. T of u is less or equal to t of v. Okay. Now how to calculate this? We have t of u, or we calculate t of v minus t of u, that should be positive. We calculate t of v minus t of u. Okay, we show that this is a positive number, that will give t of u is less than t of v. This is equal to total variation of the function f. Total variation this is equal to total variation of f over the interval av, okay, plus it's minus sign here because t is the total variation. Okay, t is total variation function, t is total variation. Minus total variation of f over the interval au, and u is less than v. Okay, u is less than v. And this we show that this is positive actually. This number is a positive number. And this is actually the total variation over u to v. This is actually total variation over u to v. This is equal to total variation over a to v minus total variation over a to u, which is equal to total variation over u to v actually. But I want to see it precisely. If I will write here plus total variation over u to v and minus total variation over u to v minus plus u to v, then minus will be u to v minus a. Okay, so I will write this as it's equal to total variation of f over the interval a to v, okay, minus total variation of f over the interval a to u. Then I will write minus again total variation over u to v, total variation minus total variation of f over the interval u to v, and I will add the same number here, total variation of f over the interval u to v. I am adding and subtracting the same number. So this is total variation of f over a to v minus total variation of f over a to u, which is equal to total variation of f over a to v minus total variation of f over a to, that's same. Then I have written here minus total variation of f over the interval uv plus total variation of f over the interval uv. This. Okay. And this is equal to total variation of f over the interval what's this over the interval a to v over the interval a to v. Then I will write here minus plus total variation of u to v. Okay, plus I will write this plus the last term plus total variation of f over the interval u to v. Then I will write minus times okay, minus times these two, minus times tvf au and minus tvf uv. It's minus times tvf au, okay, tvf au plus total variation of f over uv. Okay, you can see it. This is equal to, now look at this, it's total variation over a to u plus total variation over u to v. So this is equal to total variation over a to v. By that formula, total variation over a to b is same as total variation over a to c plus total variation over c to b. And here it's total variation over a to u plus total variation over u to v. Therefore it will be equal to total variation over a to v, because this function t is a downward variation over the interval a to v also. So this is equal to total variation of f over the interval a to v plus total variation of the function f over the interval u to v of the function f, this is tv of f, and then minus times this is total variation of f over the interval a to v. These two will go, okay, this and this. This is equal to total variation of the function f over the interval uv, but total variation is always a non-negative number because it is the sum of the modulus. Actually it's greater or equal to 0. So thus we have seen that this difference, this difference we have seen that we have seen that this different T of V minus T of U, it's greater or equal to 0. Okay, so therefore T of U minus T of V is greater or equal to 0, which implies that T of U is greater or equal to T of V, or you can say that T of V is less or equal to T of U. So therefore whenever V is less than U, T of V is less or equal to T of U. So therefore T is monotonic increasing. Monotonic increasing function. Okay, next we show that this f of x minus tx is also monotonic increasing. Exercise. Okay, let f from a b to r be of bounded variation, be of bounded variation function, and t from a b to r be the total variation function that we already defined. Be the total variation function, be the total variation function. Then show that this f of x minus t of x is monotonic increasing, is monotonic. T, we have seen that t is monotonic increasing, t of x is monotonic increasing, but we now show that fx minus tx is also monotonic increasing. For this we'll see that we'll take the crudest partition of the interval uv. Okay, so let u comma v belongs to the closed interval a b such that u is less than v. Okay, we show that fu minus tu is less or equal to fv minus tv. Let's denote this function by say h. Okay, let's denote this by hx. We'll show that h of u is less or equal to h of v. Okay, we show that this h of u is less or equal to h of v. H of u is less or equal to h of v. This we show this. Okay, where h is equal to f minus t. So what we do, we take the crudest partition of the interval AB. So let crudest means the partition which contains only 2 points, the end points of the intervals. Okay, in general this partition contains more than 2 points, but it should contain at least 2 points. That's the end points of the interval B. The crudest partition of the interval uv. So we have to take the partition of this interval. This is the interval uv. Okay, uv. We choose any number of points in between these two, or we choose only these 2 points in the partition. This is the partition P containing only 2 points u and v. It is also the partition, and this is called the crudest partition. This we call the crudest partition of this interval uv. Let's take this one. We don't have the partition smaller than this one. Okay, because every partition must contain these 2 points. So let's take this partition as this is the partition of the uv. Then f of u minus f of v. This is always less or equal to mod, because this may be negative number, but mod is always a positive. If it is positive, then equality holds. But this is the variation of the function f over the interval uv with respect to the partition uv, because this partition contains only 2 points. Therefore, in this partition, the variation with respect to this partition containing only one term, that is this one. So this is actually the variation of the function f over the interval uv with respect to the partition p. Okay, and this is always less or equal to its total variation, because the total variation is the supremum over all the partition. This is less or equal to the total variation of the function f. This is tv, sorry, total variation of the function f over the interval uv. So f of u minus f of v is less or equal to total variation of the function f over the interval uv, and this we have already seen that this is the total variation of the function f over the interval a to v, over the interval a to v minus over the interval a to u. So this is equal to this we have seen that it's equal to, this is equal to total variation of the function f over the interval a to v minus total variation of the function f over the interval a to u. This we already see. This total variation over the interval uv is equal to this. If you want to look at again here we have seen it, this one, okay, this total variation v over uv, it's actually equal to the total variation, if you go back, this total variation over uv, it's equal to this total variation over av minus total variation over au. Okay, this I'm using here, okay, so this is what I'm using, actually total variation over uv, it's equal to total variation over av minus total variation over au. Okay, so this means that this implies, so I will transfer this one tv av on this side, left hand side, and I will transfer fe, which is on the left hand side, I will transfer it on the right hand side. Okay, so this is equal, this implies, and here we have less or equal to sign. Okay, this implies f of u minus total variation okay, this is f of u minus f of v, total variation over a to u is less than v, over a to u minus over a to, it's over u to v. Okay, this is fine, over a to u, this is a to v fu plus okay, so actually I have to show that their sum should be not the difference. Actually, this fx plus tx, I have to show that fx plus tx is this function fx plus tx is monotonic increasing, where tx is the total variation function, not minus sign. Okay, not minus sign. Fine, this is a f of v, total variation of f over a to v is less or equal to, then it is f of sorry, it's here a to u. Okay, it is here a to u. It's less or equal to f of v plus total variation of the function f over the interval a to v. Okay, let me go back again. The f of u, then I have transferred this tv f a u on this side, it will be f of u plus this, and I have transferred f of v on this side, so it will be here f of v plus tv FAV. Okay, so this is fine, but this is your H of U. This is your H of U is less or equal to H of V, because H of U is F plus T. Or you can say this implies F of U plus, this is denoted, this is a function T of U, total variation, is less or equal to F of V plus T of V, and F of U plus T of U is equal to H of U. F of V plus T of V is equal to H of V, because Fx plus Tx is denoted by Hx. So thus H is monotonic, and thus this function F of x plus T of x is monotonic, while T of x is total variation function, is monotonic increasing, is monotonic increasing function. Okay, so next we have Jordan's theorem. Next theorem is the Jordan's decomposition theorem. Okay, Jordan's decomposition theorem. Jordan's decomposition theorem. A function, its statement is a function f from closed interval a b to R is of bounded variation, is of bounded variation if and only if it is the difference of two increasing function. It is the difference of two increasing functions. Proof. Now proof is very simple. Suppose f from AB to R be a bounded variation, be of bounded variation, then as we have seen that then for any x belongs to the interval AB, the function is total variation of f over the interval ax, which we have denoted by T of x, capital T of x. This function and this function f of x plus tv f ax are monotonic increasing, or increasing functions, are increasing. This we have seen, and we can write this f as f of x is equal to f of x plus tv f a to x minus tv f a to x. So we can write this in brackets here, this one. So fx can be written as difference of two functions, and both are monotonic increasing. So whenever f is a bounded variation, then f can be expressed as the difference of two monotonic increasing functions. Two monotonic increasing functions. Now we prove its converse. Conversely, assume that f is equal to g minus h is a difference of 2 increasing functions. G and h are increasing. Okay, here G and h are increasing function. We show that f is a boundary variation. We show that f is of bounded variation. So for this we need to show that its total variation is finite. So therefore we have to find its total variation actually. So in order to find its total variation, we need to find its variations actually, set of variations. So to find its variations, we choose any partition. So let's choose any partition. Let's choose any partition P, which is equal to a x0 x1 up to xn. Let's choose any partition P equal to a equal to x0, that first partition point, x1 so on up to xn. B any partition any partition of AB. Then we have, now we find its variation with respect to this partition. Then we have variation of f over p, which is equal to summation I runs from 1 to n mod of f of xi minus f of xi minus 1. Okay. Now I will write this f is equal to g minus h. This is equal to summation I runs from 1 to n. F of xi is equal to g of xi minus h of xi, because this f is equal to g minus h. Okay. Then minus times f of xi minus 1, which is equal to g of xi minus 1 minus h of xi minus 1. Okay. Then this is mod. This is equal to the summation I runs from 1 to n mod of g of xi minus g of, let's club this g function. Okay, g, okay, the terms of g of xi minus 1, this one. Then minus is plus, or you can write it as minus times also, minus times h of xi minus h of xi minus 1. Okay. Now we apply the triangular inequality. This is mod of a minus b actually, which is less or equal to mod of a plus mod of b. It's less or equal to summation I runs from 1 to n mod of g of xi minus g of xi minus 1 plus mod of h of xi minus h of xi minus 1. Now we can separate this sum. This is equal to summation I runs from 1 to n mod of g of xi minus g of xi minus 1 plus summation I runs from 1 to n mod of h of xi minus h of xi minus 1. Okay, this one. But since g is monotonic and increasing, this sum, this mod of the sum, which is already seen that it's equal to g of b minus g of a endpoints. And this is also monotonic increase. It is equal to h of b minus h of e. So thus we have seen that this, therefore this total variation, this variation for any partition p, it's independent of the partition actually. It's this number g of b minus g of a plus h of b minus h of a for any partition p of ab. So let's apply the supremum on both sides. This implies or you can say this is the upper bound of the set of all variations. Therefore the total variation must be less or equal to this. So this implies the supremum of variations of f over p is less or equal to g of b minus g of a plus h of b minus h of a, which is a finite number. So that means the total variation of f is finite. So which implies f is a bounded variation. F is a bounded variation. Okay, the function f is a bounded variation. So this proves the theorem completely. The function f is a bounded variation. So next we will show that any function which is differentiable and its derivative is bounded, then that function is a bounded variation. Do this exercise first. Let f from a b to r be differentiable, be differentiable and this f dash is bounded. F dash is its derivative is bounded. Show that f is a bounded variation. Show that f is of bounded variation. Solution. Since f dash is bounded, so therefore there is k positive number such that mod of f dash x is less or equal to k for all x in the interval a b, which implies minus k less or equal to f dash of x less or equal to k for all x belongs to the interval a b. So this implies f dash x plus k, f dash x plus k is greater or equal to 0 for all x, or you can choose k so large such that you can choose k so large such this is strictly. You can do this. This is not too difficult. Okay, this we can do. Strictly positive. Okay. This is less than, now it's greater than. Okay, f dash x plus k is greater than for all x belongs to the interval ab. Now this is very important here. F dash x plus k is positive for all x belongs to the interval ab. Now let's see this. Now we can write this. Right now we can write f of x is equal to f of x plus kx and minus kx. See these two functions, fx plus kx and this kx. We'll show that this kx is monotonic inequality because k is a positive number and k times x is monotonic inequality. Clearly, now this can be written, this is equal to g of x minus h of x. where this g of x it's equal to f of x plus kx, k into x. Okay, it's not k of x, sorry, it's product here. K is constant. K is constant, it's kx, and h of x is equal to kx. So clearly h is monotonic increasing. Clearly h is monotonic, or you can simply say increasing. Now we show that this g is also monotonic increasing. Now g of x, which is equal to f of x plus kx, this implies g dash x it's equal to f dash x plus k, which is a positive. Here we have already seen this. This is positive. F dash x plus k is positive. So this is a positive number actually. This is positive. So which implies its derivative is positive. Therefore, g is monotonic increasing. This implies g is monotonic. So thus f can be expressed as the difference of thus f can be expressed as the difference of two increasing functions. And hence by previous theorem f is a boundary variation. Hence by previous theorem f is a bounded variation. F is a bounded variation. Therefore, any differentiable function such that its derivative is bounded is a bounded variation. If the derivative of the differentiable function is a bounded function, then the function is a bounded variation. Okay, thus we have seen that a function is a bounded variation if and only if it's a difference of two increasing functions. So this is a very important class because it forms the vector space as the collection. If we denote, suppose let capital I denotes a collection of all increasing functions and capital D denotes a collection of all decreasing functions, then this I and D, it's not closed with respect to the negative scalar multiplication. It's closed with respect to negative scale, that's true, but it's not closed. Then it's not a vector space, because if f is in this, if f is either increasing or decreasing and g is either increasing or decreasing, then f1 is g. It's in general, it's neither increasing nor decreasing, so it's not in this class. This function, but this function is a bounded variation. So thus we have constructed a new collection of functions, that's called the collection of bounded variation functions, which is closed with respect to this operation. If f is a bounded variation, g is a bounded variation, then f minus g is obviously a bounded variation. You can apply this theorem. Actually, a function is a bounded variation if and only if it is difference of two increasing functions. Now here, since f is a bounded variation, g is a bounded variation, therefore f can be written as difference of increasing functions, g can be written as difference of two increasing functions. Thus f minus g can also be written as the difference of two increasing functions. Therefore f minus g is a bounded variation. But this function is neither monotonic increasing nor monotonic decreasing. It is not in this class. So this is the nice extension of the collection. This collection of monotonic increasing, monotonic decreasing functions. It's a nice extension because it forms the vector space. Now you can easily verify the vector space properties of this collection. The collection of all bounded variation function will be denoted by over the interval AB. It is denoted BV of AB. So this collection of all bounded variation function, it forms a vector space. So this is very important structure now. So you can easily verify its vector space properties. It's closed with respect to addition, it's closed with respect to scalar multiplication, and you can also check the rest of the properties. It's a vector space over R, okay, over the real line R. So that's why this structure is this is very nice. This is a very nice extension of this collection. This collection does not have such a nice structure. Okay. Now next we have an example in which we show that this function is not a, as we have already seen that the function f of x, which is equal to x cos of pi by 2x, if x is not equal to 0 and it's equal to 0 if x is equal to 0. This function is not a boundary variation. Now we have here another function f of x equal to x square cos of 1 over x square. Okay, if x is not equal to 0 and it's equal to 0 if x equal to 0. So you show that this function is also not a boundary variation. Here you have chosen the partition points like this. You're choosing this part 0, 1 by 2n, then 1 by 2n minus 1, so on 1 by 3, 1 by 2, 1 by 1. And then you have seen that the variation with respect to this partition is actually the sum 1 plus 1 by 2 plus 1 up to 1 by n. Therefore the supremum is an infinite number. And now here what partition you will choose actually. So you have chosen a partition in such a way that this number is equal to 1. After substituting x, the value 1 by 2n, here it will be 1 by 2n, 1 by 2n, it will be n pi, which is equal to minus 1 power n, but you are in under mod, therefore it is equal to 1. And same you have to do here, so that if we substitute x square, say first partition you will choose 0. And what will be the second partition point? So that when we substitute that point in this function, it will be plus 1 or minus 1, then we have a mod here, so it's always equal to plus 1. But how do we do that? Let's if we choose this partition, 1 by root of pi n, okay, just fine, root of pi n, 1 by root of pi n, is that okay? 1 by root of pi n, you check this one, 1 by root of pi n, okay, root, or you can say n pi, and then n minus 1 pi, 1 by root of pi times n minus 1, and so on. You choose 1 by root of 2 pi, then finally you choose 1 by root of pi. Okay, let's choose this partition of the interval 0 to 1 by root of pi. So with respect to this partition, you will see this the variation with respect to this part. It's like this. It's like the sum, this 1 plus 1 by 2 plus 1 by 3 plus 1 plus 1 by n, and you will see that sum, the supremum of those variations is an infinite number. So you check this. Okay, I'm not sure about whether we choose this partition or not, but this is an exercise for you. You will see with respect to this partition what will happen. The variation, what will be its variation with respect to this partition. You'll check, please check this one, or you can if you'll face any problem, you change this partition accordingly. Okay, so this is it, and similarly you can see this function, one more exercise is here. Let's f of x equal to x square cos of 1 by x, x not equal to 0 and it's equal to 0 if x equal to 0. It's a differentiable function. Here we will see its derivative. What's its derivative? If its derivative is finite, then it's a boundary variation. Its derivative is equal to twice x into cos of 1 over x. Okay, the interval is here 0 to 1. We have to check it over this interval. Then what's the differentiation of cos? It's minus, so minus x square, as it is differentiation of cos is minus. That's why here I have here minus sign here. It is sine of 1 over x into differentiation of 1 over x, that's equal to minus 1 over x square. So this should be plus now 1 over x square. This x square will go. It's equal to twice x cos of 1 over x plus sine of 1 over x. but sine function is always bounded, cos is always bounded, x is also bounded by 1. So you can see this mod of f dash x, it's equal to mod of this, which is less or equal to mod of this, but mod of it's less or equal to 2 plus 1, you can see, because mod of cos of 1 over x is less or equal to 1, and mod of x is also less or equal to 1 because x belongs to the interval 0 1. So it's twice 1 into 1, that's 2. This is less or equal to 1, it's plus 1 less or equal, that's equal to 3. So therefore the derivative of this function is bounded, and it's a differentiable function also, its derivative is bounded, therefore it is a bounded variation. It's a bounded variation. So thank you. Next we'll take the new